Tonight, we embark on a journey towards something we encounter in every single moment of our lives. This is an element of our world so common that we seldom give it a second thought. Yet it is also so profoundly strange that physicists are still debating its most fundamental nature. We are, of course, talking about light, and more specifically, about the very thing that constitutes it, the photon. The photon, as a concept, presents us with a series of bewildering paradoxes. It is an entity that possesses no mass, and yet it is a carrier of energy. It travels at the ultimate cosmic speed limit, 300,000 kilometers per second. Yet from its own unique perspective, its journey is entirely instantaneous, experiencing no passage of time whatsoever. It can manifest either as a particle or as a wave, with its identity appearing to shift based on the very act of observation. Perhaps the most bizarre quality of all is that a single photon seems capable of interfering with its own path, as if it can somehow exist in two separate locations at the exact same time. As we explore this topic, you will begin to appreciate why Albert Einstein described the photon as physics' greatest enigma, and why its mysteries seem to multiply with each new discovery. If this kind of deep exploration into the fundamental nature of reality is something that resonates with you, supporting Calm Space with a like or a subscription is what helps us continue to create this content. Now, let us begin our investigation. Let us begin with what feels self-evident. When you flick a switch, a room is instantly bathed in light. When you stand outside on a clear day, the sun's rays deliver warmth directly to your skin. And when you gaze up at the night sky, you are seeing starlight that has journeyed for billions of years across incomprehensible voids just to finally meet your eyes. In the context of our daily lives, light appears to be straightforward. It illuminates our surroundings, enables vision, and sustains life itself. We are so immersed in it that we rarely pause to consider what it is. Yet, for millennia, humanity had no true concept of light's identity. Even today, following centuries of scientific progress after the revolutions of quantum mechanics and relativity, and after some of the most precise experiments ever, devised light stands as one of the most peculiar phenomena in the cosmos. The more deeply we investigate light, the more alien it seems to become. Its fundamental particle, the photon, operates in ways that completely defy our common sense, challenging our most basic assumptions about the nature of reality and forcing physicists to discard intuitions that have served humanity for its entire history. This is the story of how we unveiled the true nature of light, and why that ultimate reality proved to be far more peculiar than anyone could have ever predicted. The ancient Greeks, naturally, had their own theories about light, being the first culture to systematically examine natural phenomena through the lens of reason rather than myth. Plato, for instance, proposed that our eyes actually emitted a form of light, which would then reach out to touch objects, thereby allowing us to perceive them. In his conception, vision was an active process, one where rays sent out from the eye gathered information about the world and then returned it to the mind. While this idea may sound absurd to a modern ear, it did align with certain subjective human experiences. We still use phrases such as casting a glance, as if our gaze possesses a physical presence, or we say that someone's eyes lit up, as if the source of illumination is internal. Plato's theory was, of course, ultimately incorrect, but it did manage to capture something essential about the human experience of seeing. This simple observation serves to highlight how our language can preserve these ancient, intuitive ideas long after science has moved past them. Aristotle, who was Plato's student, held a distinctly different view. He theorized that light was not an emission from the eye, but was instead a disturbance within the medium that exists between the eye and the object, being viewed a concept similar to a wave moving through water or air. Aristotle had observed that a straight stick submerged in water appears to bend at the surface, a phenomenon we now call refraction. He had recognized that the behavior of light changed as it moved between different substances. His proposal was that transparent materials such as air, water, and glass contained a certain potential to transmit light, and that the presence of actual light was simply the activation of that potential. Lighting a lamp, in this view, therefore activated the transparency of the surrounding air, which allowed this activation to spread out instantaneously. And although neither of these early Greek explanations was ultimately accurate, they successfully established the central conflict that would go on to define the next 2,000 years of scientific inquiry. What exactly is light? Is it a stream of particles, a propagating wave, or perhaps something else entirely that fits neatly into neither of those categories? The stage was thus set for a fundamental debate that would continue to echo for more than 2 millennia. For the many centuries that followed, humanity's understanding of light advanced at a very slow pace. The Romans, for example, being practical engineers, were far more concerned with using light than with defining it. They constructed lighthouses, employed mirrors for signaling, and operated on the principle that light travels in straight lines. It was the medieval Islamic scholars who would make the next significant leaps forward in the field of optics. Around the year 1000, the scholar Ibn al-Haytham, working in Cairo, managed to definitively disprove Plato's emission theory of vision. His logic was both simple and elegant. He argued that if our eyes truly emitted light, then we should be able to see in complete darkness. Since we are unable to do so, light must therefore originate from external sources and enter our eyes, not the other way around. But even this crucial step forward still left the central mystery completely untouched. What, exactly, was this light that was entering our eyes? Then, in the 1600s, two towering figures in the world of science presented competing theories that would frame the entire debate for centuries to come. On one side of this debate stood Isaac Newton, who is arguably the most influential scientist in all of history. Newton championed the idea that light was composed of infinitesimally small particles, which he gave the name corpuscles. He argued that these corpuscles were ejected from light sources and then traveled in perfectly straight lines until they eventually collided with an object. This model neatly explained why light casts such sharp, well-defined shadows. Particles moving in a straight path would naturally be expected to create crisp borders between illuminated and dark areas. Newton's corpuscular theory also appeared to align with other everyday observations. For instance, light reflects from mirrors, much like a ball bounces off a wall, and it can be focused by a lens in a way that is entirely consistent with particles following a curved trajectory. When Newton published this theory in his 1704 book, Optics, his already immense reputation ensured that it was taken with the utmost seriousness. After all, he had already transformed the field of physics with his laws of motion and universal gravitation, and had also co-invented calculus. When Isaac Newton spoke, the entire scientific establishment listened. This raises a key question in the history of science. Just how much does the reputation of a scientist influence the acceptance of their ideas? On the other side of this great debate was Christiaan Huygens, a brilliant Dutch scientist who argued that light was, in fact, a wave. Huygens proposed that light propagated through space as a form of vibration in some unseen medium, much in the same way that sound travels through the air. When a person speaks, for example, their vocal cords vibrate, which creates pressure waves in the air that travel to a listener's ear, causing their eardrum to vibrate in turn. Huygens suggested a very similar mechanism for light. A source like the sun or a candle flame would initiate vibrations in a mysterious, unseen medium, and these vibrations would then ripple outward until they finally reached an observer's eye. This wave-based perspective, however, offered compelling explanations for certain behaviors of light that the particle model found particularly difficult to address. When light is forced through a very narrow opening, it exhibits a curious behavior, spreading out slightly around the edges. This phenomenon, known as diffraction, is a defining characteristic of waves. We see this same principle in action all around us. Sound waves, for instance, can bend around corners, which is why you can hear a conversation in an adjacent room without a direct line of sight. Similarly, ocean waves fan out after passing through a gap in a seawall. If light behaved in the same way, it raised a profound question. Could light itself be a wave? For more than a century, this idea competed with the theory proposed by Isaac Newton, who argued that light was composed of tiny particles, or corpuscles. Newton's immense prestige, especially in his native England, ensured his theory held sway, while the wave theory found more supporters on the European continent, where Christian Huygens' work was highly regarded. The debate seemed intractable, as both models could explain certain aspects of light's behavior, but neither could account for everything. This scientific impasse was seemingly broken in 1801, thanks to an experiment by the British scientist Thomas Young. His setup was a model of simplicity and elegance. Young directed a beam of light toward a barrier containing two extremely narrow, parallel slits placed very close to each other. He then observed the pattern the light created on a screen positioned behind the barrier. If light were truly made of particles, as Newton suggested, the outcome would be predictable. One would expect to see two distinct bright bands on the screen, directly corresponding to the two slits, much like firing bullets through two holes in a wall would result in two clusters of impact. The logic was straightforward, and the expected outcome seemed intuitive. However, the result Young witnessed was entirely different and far more complex. Instead of two simple bright lines, the screen displayed a series of alternating bright and dark bands, an interference pattern that stretched across a much wider area. This was not the behavior of particles. This pattern is a hallmark of waves and can only be produced by them. The observation suggested that the fundamental nature of light was not what the particle theory predicted. To visualize what was happening, one can imagine dropping two stones into a calm pond. Each stone generates a series of concentric ripples that travel outward. Where these two sets of ripples intersect, a complex pattern emerges. When the crest of one wave meets the crest of another, they combine to form a larger wave in a process called constructive interference. Conversely, when the crest of one wave encounters the trough of another, they cancel each other out, resulting in a patch of still water. This is known as destructive interference. The pattern of bright and dark stripes Young observed on his screen was a perfect optical analog to this phenomenon. The light passing through the two slits was behaving like two distinct wave sources. In the areas on the screen where the wave crests from each slit arrived in sync, they created bright bands of constructive interference. In the regions where a crest from one slit met a trough from the other, they cancelled out, producing the dark bands of destructive interference. Young's double-slit experiment appeared to be conclusive proof that light was a wave. The corpuscular theory seemed to have been definitively refuted. After all, particles do not interfere with one another in this way. They simply collide or pass by. Only waves could create such a pattern, and Young had shown that light did exactly that. For all intents and purposes, the case seemed closed. For the following 100 years, the wave theory of light became the undisputed foundation of optics. Physicists developed sophisticated mathematical frameworks that precisely described light's wave-like behaviors, including how it reflects from surfaces, refracts when moving between different media, diffracts around obstacles, and interferes with itself. This theory was powerful and elegant, successfully explaining a host of observations that the particle model could never accommodate. Yet, even within this triumph, a critical and perplexing question lingered. If light was a wave, what was it a wave times in? This question of a medium became increasingly pressing. Sound waves are pressure vibrations that propagate through a medium like air. Water waves are oscillations that travel across the surface of water. But light from the sun reaches Earth after traversing 93 million miles of what appears to be empty space, and light from distant stars crosses even more immense voids. If light was a wave, it seemed to require something to carry its vibrations. The vacuum of space presented a significant conceptual problem. To resolve this paradox, scientists proposed the existence of a theoretical, all-pervading substance they named the luminiferous ether. This invisible, undetectable medium was thought to fill the entire universe, permeating every corner of space, including the vacuum between celestial bodies. Light, they reasoned, was simply a vibration propagating through this cosmic ether. It was a necessary component to make the wave theory of light work. However, the proposed properties of this ether were deeply contradictory. To support the incredibly high frequency and speed of light waves, which travel at 300 million meters per second, nearly 1,000,000 times faster than sound in air, the ether had to be extraordinarily rigid, far stiffer than steel. At the same time, it had to be completely transparent and imperceptible, since we cannot see or feel it. Furthermore, it needed to be so tenuous that planets could orbit through it for eons without any detectable friction or slowing. How could a substance be both unimaginably stiff and yet offer zero resistance to motion? The concept was fraught with internal contradictions. Despite these challenges, the existence of the ether seemed a logical necessity based on the knowledge of the time. The argument was simple. All known waves require a medium to travel. Light had been proven to be a wave. Therefore, light must have a medium. This line of reasoning locked physicists into the concept of the ether for decades. It was in the 1860s that a Scottish physicist, James Clerk Maxwell, made a discovery that would ultimately reshape this entire understanding. In what stands as one of the greatest achievements in the history of science, Maxwell began to unify the phenomena of electricity and magnetism. Before his work, these were considered two separate forces. Electric charges produced electric fields, and magnets generated magnetic fields. Maxwell's efforts would set the stage for the next great revolution in our understanding of light. While electric currents could produce magnetic effects and shifting magnetic fields could generate electricity, the precise nature of their connection remained a puzzle. The two phenomena seemed related, yet distinct. It was James Clerk Maxwell who demonstrated that they were, in fact, profoundly intertwined, not separate forces, but two facets of a single entity, the electromagnetic field. In his model, a changing electric field gives rise to a magnetic field, and a changing magnetic field, in turn, creates an electric field. This creates a self-perpetuating cycle, a dynamic interplay in which each field sustains the other. When Maxwell formalized this relationship with a set of equations, he uncovered something truly extraordinary. His mathematics predicted the existence of waves formed by oscillating electric and magnetic fields that would propagate through space at a very specific velocity. An oscillating electric field would generate a magnetic field, which in turn would then oscillate and regenerate the electric field. This self-sustaining disturbance would travel forward, carrying energy along with it. What made this discovery so stunning was the speed his equations yielded. Maxwell calculated this velocity using two fundamental constants of nature: the permittivity of free space, which determines the strength of electric fields, and the permeability of free space, which governs magnetic fields. These were values that could be measured in a laboratory with basic equipment, seemingly unrelated to the study of light. When combined, they produced a speed of approximately 300,000 kilometers per second, a figure that proved to be virtually identical to the measured speed of light. The proximity of these two values was too remarkable to be a mere coincidence. Maxwell drew the inevitable conclusion that light itself must be an electromagnetic wave. It was a self-propagating oscillation of electric and magnetic fields moving through the cosmos at the exact speed his equations had foretold. He had not set out to build a theory of light. His primary goal was to understand electricity and magnetism. Yet, the logic of his mathematics led him to one of the most profound unifications in the history of science. This powerful insight revealed that light was not some unique phenomenon. Instead, it was just one part of a much broader electromagnetic spectrum that includes radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. Fundamentally, all of these are the same thing: electromagnetic waves, differentiated only by their frequency and wavelength. For instance, red light has a longer wavelength than blue light, at roughly 700 nanometers compared to 450 nanometers. At the far ends of the spectrum, radio waves possess wavelengths that can be measured in meters or even kilometers, while gamma rays have incredibly short wavelengths, smaller than the nucleus of an atom. And yet, all of them travel at the same constant velocity, the speed of light. The familiar rainbow of colors we perceive is just a tiny sliver of this immense spectrum, corresponding to the specific frequencies that our eyes have evolved to detect. Maxwell's theory also appeared to resolve the long-standing problem of the luminiferous ether, an electromagnetic wave being a self-sustaining interplay between its electric and magnetic components, did not seem to require a physical medium through which to travel. It could propagate through the vacuum of empty space. This was a revolutionary concept, as it was the first time physicists could conceive of a wave that needed no material to carry it. With this elegant solution, the theory seemed complete. The centuries-old debate over whether light was a particle or a wave seemed to be definitively settled in favor of waves. The scientific community, now confident that the nature of light was finally understood, began to move on to other challenges. However, as the 19th century gave way to the 20th, new experimental findings began to surface that could not be explained by Maxwell's otherwise triumphant theory. These emerging anomalies would compel physicists to re-examine everything they thought they knew about light. The first of these puzzles was a phenomenon known as black body radiation. When any object is heated, it begins to glow. A piece of iron in a forge, for example, will first glow a dull red, then shift to orange, yellow, and finally white as its temperature increases. This relationship between temperature and the color of the emitted light is so consistent that astronomers rely on it to measure the surface temperatures of stars trillions of miles away. Classical physics, which combined Maxwell's electromagnetic theory with the laws of thermodynamics, offered a prediction for how much light a heated object should radiate at every wavelength. On the surface, the reasoning seemed sound. A hot object is full of vibrating atoms, and these oscillating charges should produce electromagnetic waves across a continuous spectrum of frequencies. The hotter the object, the more energy it has, and therefore the more light it should emit. However, the predictions of this classical model failed spectacularly when compared to reality. The calculations showed that hot objects should release progressively more energy at shorter and shorter wavelengths. As one calculated the expected energy output in the ultraviolet, X-ray, and gamma ray portions of the spectrum, the predicted energy rose without any limit. This theoretical outcome was so contrary to experience that it was nicknamed the ultraviolet catastrophe. According to the theory, a simple hot oven should be emitting infinite amounts of energy at short wavelengths, flooding the surrounding area with deadly gamma rays. Of course, this is not what happens in reality. Something was fundamentally wrong with the calculation. In 1900, the German physicist Max Planck discovered a solution to this problem, but it was a proposal that he himself found strange and deeply unsettling. Planck suggested that energy is not a continuous, fluid quantity, as had always been assumed. Instead, he posited that energy is emitted and absorbed in discrete packets, which he named quanta. The energy of each individual quantum, he proposed, was directly proportional to the frequency of the radiation. High-frequency light, like ultraviolet, would consist of large, high-energy quanta, while low-frequency light, like red light, would be made of small, low-energy quanta. By incorporating this idea of quantized energy into his calculations, Planck was able to derive a new formula that perfectly matched the observed spectrum of black-body radiation. With this adjustment, the ultraviolet catastrophe vanished. At high frequencies, the energy quanta was so large that the random thermal vibrations within a hot object simply didn't have enough energy to produce them. His theory now fit the data perfectly, but the cost was a radical new idea about the nature of energy itself. Even Planck was not entirely convinced of the physical reality of his own idea. He initially regarded his quantum hypothesis as little more than a kind of mathematical trick, a useful calculational tool that just happened to produce the correct answer. The notion that energy existed in discrete chunks was too extreme to be taken literally. For centuries, energy had been treated as a continuous variable, capable of being divided infinitely and taking on any possible value. Surely, Planck must have thought, this quantum concept was merely a convenient fiction and not a true description of how the universe actually worked. But this mathematical trick was about to open the door to a new and even stranger reality. Max Planck's idea of energy quanta was just the beginning, and it would soon find powerful new applications. The next major challenge to classical physics arose from a phenomenon known as the photoelectric effect. This effect, first documented in the 1880s by Heinrich Hertz during his experiments with electromagnetic waves, occurs when light strikes a metal surface and causes it to eject electrons. On the surface, this seemed like a problem that classical wave theory should easily solve. After all, light waves are carriers of energy. It stood to reason that this energy would be absorbed by electrons within the metal, eventually providing them with enough of a boost to escape the surface entirely. According to this classical wave model, the brightness of the light should be the most important factor. A brighter light carries more energy, so it should eject more electrons and give them more kinetic energy. Furthermore, if a very dim light were used, the theory predicted a delay. An electron would need time to gradually accumulate enough energy from the faint, continuous wave before it could be liberated. The dimmer the light source, the longer this accumulation period was expected to be. But did the experimental evidence actually support this intuitive picture? The reality observed in laboratories was starkly different and defied classical predictions. Experiments demonstrated that electrons were ejected from the metal surface instantaneously, even when the light was incredibly dim. There was no measurable time lag for energy to build up. Even more perplexing was the discovery that the energy of the ejected electrons was determined not by the light's brightness, but by its color. Blue light, for example, would dislodge electrons with more energy than red light, regardless of how bright the red light was. This observation was a direct challenge to the wave model. In fact, the experiments revealed a critical threshold. If the frequency of the light was too low, if the light was, for instance, too red, no electrons would be ejected at all. It didn't matter how intense the light source was. One could shine an incredibly powerful red light on the metal for hours, and not a single electron would emerge. Yet, a faint beam of blue light would begin ejecting electrons the moment it hit the surface. From the perspective of wave theory, none of this was logical. A more intense wave should always deliver more energy, and any wave, given enough time, should eventually deliver the required amount. Something was fundamentally wrong with the classical understanding of light. Then, in 1905, a revolutionary solution was proposed by Albert Einstein, who was working as a patent clerk in Switzerland at the time. Taking Planck's concept of energy quanta to its logical conclusion, Einstein suggested that light itself was not a continuous wave, but was composed of discrete particles. Each of these particles, which he termed light quanta, and we now call photons, carried a fixed amount of energy directly proportional to its frequency. This single, bold idea could explain the photoelectric effect with remarkable precision. In Einstein's model, the interaction between light and matter becomes a one-on-one event. When a single photon strikes an electron, it transfers all of its energy in an instant, an all-or-nothing transaction. If that photon possesses sufficient energy, which is determined by its frequency or color, the electron absorbs the energy and escapes the metal. If the photon's energy is below the required threshold, the electron absorbs nothing and remains in place. There is no gradual accumulation of energy. This explains why color is more significant than brightness. Blue photons, having a higher frequency, carry more energy than red photons. A flood of red photons, each individually lacking the necessary energy, will never eject an electron. However, even a single blue photon, with enough energy, can free an electron instantly. While Einstein's explanation elegantly matched the experimental data, it also created a profound conceptual crisis. It seemed to directly contradict more than a century of evidence, suggesting that light behaves as a wave. Thomas Young's double-slit experiment, for instance, had produced interference patterns that could only be explained if light were a wave. Particles, as they were understood, do not interfere or cancel each other out. They simply accumulate. This set the stage for one of the most perplexing periods in the history of science. Light, it appeared, was somehow both a particle and a wave, depending on how it was observed. This wave-particle duality presented a seemingly impossible paradox. The two concepts are fundamentally incompatible. A wave is a disturbance that spreads out, occupying a wide region of space and interfering with other waves. A particle is a localized object, existing at a single point and colliding with other particles. Yet, light demonstrated both sets of properties. In some experiments, it behaved precisely like a wave, diffracting around obstacles and creating interference patterns. In others, it acted like a stream of particles, ejecting electrons one by one with discrete packets of energy. The behavior it exhibited seemed to depend entirely on the nature of the measurement being performed. This puzzle would occupy physicists for decades, ultimately leading to the formulation of quantum mechanics. In 1921, Einstein was awarded the Nobel Prize in Physics, not for his celebrated theory of relativity, but for his groundbreaking explanation of the photoelectric effect. The Nobel Committee recognized that his work on light quanta was a pivotal development that opened the door to the quantum realm, revealing that the classical distinction between waves and particles dissolves at the most fundamental level. Ironically, even as he accepted the honor, Einstein himself was becoming deeply troubled by the strange implications of the quantum theory he had helped to create. He would spend the rest of his life searching for a deeper, more complete theory that could restore the deterministic principles that quantum mechanics seemed to violate. The name photon itself would not be formally introduced until 1926, when the American chemist Gilbert Lewis coined the term. The term photon, which is derived from the Greek word times phos, times for light, was first proposed by Gilbert Lewis, and the name was rapidly adopted by the scientific community. By the conclusion of the 1920s, the photon was accepted as a fundamental particle of nature, taking its rightful place alongside the electron and the proton. But what, precisely, is a photon? This is the point where the picture becomes genuinely strange. A photon is not a miniature bullet of light, nor is it some tiny sphere hurtling through the cosmos. Its essential nature is far more subtle and bizarre than any object familiar to us in our classical world. A photon is a quantum of the electromagnetic field, a discrete excitation of a field that permeates all of space. When we talk about a photon traveling from the sun to our eye, what we are really describing is a specific excitation in the electromagnetic field that propagates through space at the speed of light. This might appear to be a mere technicality or a philosophical distinction, but its implications are truly profound. A photon does not exist in the same manner that a rock does. It lacks any definite position in space until it is measured, and it does not follow a single predictable trajectory from its source to a detector. It exists as a cloud of probability, a quantum of potential that only solidifies into a concrete reality upon interacting with something else. The history of our quest to understand light offers a powerful lesson regarding the nature of science and human knowledge. For centuries, some of the most brilliant minds on the planet were convinced they had finally solved the puzzle of light. Isaac Newton was certain that it was composed of particles, and his mathematical framework was both elegant and highly predictive. Later on, physicists became just as certain that light was a wave. The experiments of Thomas Young appeared to be definitive, and James Clerk Maxwell's beautiful theory seemed to offer a complete and final explanation. Each generation, it would seem, thought the question was settled for good. Nature, however, still had surprises in store. The discovery of the photoelectric effect and the puzzle of black body radiation clearly demonstrated that our understanding was incomplete. The true character of light was far stranger than anyone had previously imagined. This historical journey ought to instill in us a deep sense of humility. If humanity's greatest geniuses were mistaken about something as fundamental as light, what other assumptions might we be mistaken about today? The story of the photon is far from over, and its quantum strangeness only seems to deepen the more we learn. A single particle of light can, in a way that defies conventional logic, interfere with itself, as if it passed through multiple locations simultaneously. Photons also appear to experience the passage of time in a manner that challenges our very conception of existence. In the framework of modern physics, the photon is described as one of the fundamental force-carrying particles responsible for holding the universe together. It seems the more we scrutinize this seemingly simple particle of light, the more bizarre it becomes, raising the profound question of how a single entity can embody so many contradictions. We now arrive at the truly perplexing heart of our story. We have seen that in some experiments, light behaves as a wave, while in others, it acts like a particle. Young's double-slit experiment offered compelling evidence that light was a wave. In stark contrast, Einstein's explanation of the photoelectric effect provided equally strong proof that light was a particle. Both of these landmark experiments are correct, and their results are consistently reproducible. And yet, they appear to contradict one another directly. What happens then when we design an experiment to observe this dual nature head-on? What occurs when we take Young's classic double-slit experiment, the very experiment that seemed to prove light is a wave, and conduct it with individual photons, one at a time? By stripping away any possibility of collective behavior, we can attempt to force light to reveal its true underlying nature. This specific experiment is one of the most famous in the annals of physics, and its results are so counterintuitive that they remain deeply unsettling, even to physicists who have dedicated their careers to studying quantum mechanics. Richard Feynman, one of the 20th century's greatest physicists and a Nobel laureate for his work on quantum electrodynamics, stated that the double-slit experiment contains the essential mystery of the quantum world. He argued that all of the field's strangeness, its paradoxes, and its philosophical puzzles are concentrated within this one experimental setup. If you can truly understand it, you can understand quantum mechanics. But, as Feynman also implied, nobody truly understands quantum mechanics in a way that feels intuitive or complete. Let me describe the experimental setup in detail. You begin with a light source that can be controlled to emit individual photons, one by one. Modern technology makes this possible, allowing for sources so dim and carefully regulated that they release single photons with significant time gaps between them. You then have a barrier with two narrow, parallel slits. just as in Young's original experiment. Behind this barrier is a detector screen capable of recording the precise location where each individual photon lands. Unlike the old photographic plates that simply accumulated exposure over time, modern detectors can register the arrival of each photon, marking its position and time with remarkable precision. Now, you send photons through this apparatus one at a time. You wait long enough between each emission so that the previous photon has already struck the screen before the next one is even released. At any given moment, there is never more than one photon within the entire system. This is a critical detail because it means the photons cannot possibly interact with or influence one another. Each photon undertakes its journey through the slits completely alone. The experiment is therefore designed to isolate the photon, compelling it to reveal its fundamental nature, free from any group influence. What pattern would you logically expect to see on the screen after many thousands of photons have been recorded? If photons were simple particles, like tiny bullets fired at a target with two openings, each photon would have to pass through either one slit or the other. It would travel in a straight line from the source, pass through whichever slit happened to be in its path, and continue in a straight line to the screen. Some photons would go through the left slit and land on the screen behind it. Others would go through the right slit and land somewhere behind that one. After many photons, you would expect to find two bright bands on the screen, one directly behind each slit. This is precisely what you would see if you fired bullets at a wall with two holes. If, on the other hand, photons were simple waves, the wave would spread out from the source, encounter the barrier, and pass through both slits simultaneously. A wave, by its very nature, is distributed in space and is not confined to a single path. Herein lies the central dilemma. The experiment is designed to send single, indivisible particles, yet it presents them with a choice that seems better suited for a wave. The outcome of this test is what reveals the profound and unsettling reality at the heart of the quantum world. When two waves emerge from the slits, they propagate outwards and begin to overlap in the space beyond the barrier. In areas where the peaks of the waves align, they reinforce each other through constructive interference, creating bright regions. Conversely, where a peak meets a trough, they cancel each other out through destructive interference, resulting in dark regions. This is what produces the classic interference pattern that Thomas Young first observed, a series of alternating bright and dark stripes on the screen. But this explanation is for continuous waves. What happens when we use individual particles of light, photons, sent one by one? Surely, a single particle cannot behave like a wave. This is the point where the familiar laws of physics give way to something far more perplexing. Each photon arrives at the detection screen and makes its mark at a distinct, localized point, just as a particle would. We can witness the individual impacts appearing one at a time. A single flash materializes here, then another appears over there. Every photon is registered at a specific location, confirming its particle-like nature upon arrival. Initially, this behavior aligns perfectly with our expectations for particles. However, as the number of photons increases, a surprising picture begins to form. The dots do not simply cluster into two bands directly behind the slits. Instead, they methodically assemble into a full interference pattern, the very same one Young observed with continuous light, complete with alternating bands of constructive and destructive interference. After only 10 photons have landed, their distribution appears entirely random. With 100 photons, the faint outlines of a structure might begin to take shape. Once 1,000 photons have accumulated, the interference pattern becomes clearly visible, and after millions of photons, the pattern is unmistakable and stark. This outcome presents a profound paradox. The individual, particle-like impacts have collectively organized themselves into a pattern that can only be explained by the behavior of waves. Each photon is detected as a single, localized particle, with no ambiguity about its arrival point. Yet, the final distribution of these particles is governed by the mathematics of wave interference. This implies something truly bizarre. Each individual photon seems to interfere with itself, as if it had passed through both slits simultaneously. It's crucial to appreciate just how strange this is. The photons are dispatched one at a time, ensuring that only a single photon is present within the apparatus at any given moment. There is nothing else for it to interact or interfere with, no other photons, no competing waves. There is only a solitary photon on its journey from the source to the screen. And yet, the behavior of that single photon is somehow influenced by the existence of both slits. We can confirm that the photon is aware of both paths with a simple test. If one slit is closed, leaving only a single route available, the interference pattern vanishes entirely. All that remains is a single band of impacts behind the open slit, precisely where you would expect particles like bullets to accumulate. But the moment the second slit is reopened, the interference pattern immediately returns. The photon's behavior changes dramatically when two paths are available, even though it seems that any single photon must logically pass through only one. Consider the implications. With only one slit open, photons can land in a specific area on the screen. Yet, when a second slit is opened providing an additional path to that same area, fewer photons end up there. Adding another way for them to arrive actually reduces the number of arrivals. For particles, this is impossible. Opening a second hole for bullets could only ever increase the number that reach a target, never decrease them. For photons, however, the second slit introduces interference that prevents them from landing in certain places. The standard interpretation of quantum mechanics provides an answer, but it's one that fundamentally challenges our everyday understanding of reality. According to this framework, before a photon strikes the screen, it does not possess a definite position. It doesn't travel through the left slit or the right slit in a classical sense. Instead, it is described as existing in a superposition of possibilities, effectively traversing both paths at the same time. The photon occupies a quantum state that encompasses both potential journeys simultaneously. Only upon interaction with the screen, the moment of detection, does this cloud of possibilities collapse into a single, specific position. The mathematical tool used to describe this state is the wave function. This function represents the probability of locating the photon at any given point in space. Before a measurement is made, the wave function expands, passes through both slits, and interferes with itself on the other side. The values of the wave function are high in regions of constructive interference and low in regions of destructive interference, dictating the probability of the photon appearing at any particular spot. The instant the photon is detected, the wave function collapses. The entire distributed field of probability instantaneously resolves into a single point. The photon appears in one location, and the probabilities of it being anywhere else drop to zero. Where it appears is a matter of chance, but the odds are determined by the interference pattern encoded within the wave function. This is the renowned principle of superposition. It suggests that quantum objects do not have definite properties, like position, until they are measured. Prior to measurement, they exist as a combination of all their possible states at once. A photon passing through the double-slit apparatus is in a superposition of having gone through the left slit and having gone through the right slit. These two possibilities interfere with each other mathematically, generating the interference pattern, even as each photon ultimately lands as a single particle. A skeptic might argue that this is merely an interpretation. Perhaps the photon does travel through one specific slit, and the superposition is just a mathematical representation of our own ignorance about which path it took, not a description of reality itself. This raises a crucial question. If the photon truly goes through both slits, why can't we simply look and see which path it takes? Why not place detectors at each slit to watch its journey? You can, and physicists have performed this experiment many times with ever-improving technology. The result is the most bewildering part of this entire story. If you install detectors at the slits to determine which path each photon follows, the interference pattern completely disappears. The moment you gain which path information, the photon behaves like a simple particle, and you see two distinct bands on the screen, one behind each slit. When you do not know the path, it behaves like a wave, creating the interference pattern. The very act of observation appears to determine the nature of reality. This isn't a matter of the detectors physically disturbing the photons and disrupting the experiment. The effect persists even with the most delicate measurements imaginable. To explore this phenomenon, physicists have devised a series of exceptionally clever experiments, all designed to challenge this mechanical interpretation. In some versions, detectors were engineered to interact with photons as gently as possible, creating only the slightest disturbance. Even with this minimal contact, the interference pattern vanished. In other setups, the experimental records contained the potential to reveal which path a photon took, even if no scientist ever actually analyzed the data. The outcome was precisely the same. The interference pattern disappeared. There are even experiments involving quantum erasers, which first detect the path information but then irretrievably destroy it before anyone has a chance to see it. In these cases, the interference pattern dramatically returns. The conclusion from this body of work is consistent and seems to be absolute. It raises a fundamental question about the role of information itself in shaping reality. If it is possible, even in theory, to determine which slit a photon passed through, it behaves like a particle, and the interference pattern is lost. Conversely, if there is no way to know the path, the photon acts as a wave, and the pattern reappears. This puzzle is known as the measurement problem, and it represents one of the most profound mysteries in all of physics. The simple act of measurement, or even the mere possibility of it, appears to fundamentally alter the behavior of quantum systems. But this forces us to ask, what exactly qualifies as a measurement? Is a conscious observer required to look at the result for the change to occur? Does any physical interaction, no matter how small, count as a measurement? What if an interaction records information that is never examined by anyone? For nearly a full century, physicists have debated these questions, and a definitive consensus remains elusive. To illustrate this mystery in an even more striking way, consider an experiment called the delayed choice experiment. This thought experiment was first proposed by the physicist John Wheeler in 1978 and has since been carried out in various forms, with real-world results confirming its bizarre predictions. The setup involves sending photons one by one toward a double-slit apparatus, but with a crucial twist. The decision of whether to measure which slit the photon went through is delayed until after it has already passed the barrier. This choice is made late, long after the photon should have already committed to behaving as a particle or a wave. Here's how the arrangement functions. After passing through the slits, the photon begins a journey toward a detector screen. This path is made long enough to give the experimenter time to make a critical choice while the photon is still in transit. During this flight, the experimenter can either insert a device that will reveal which slit the photon came from, or choose to leave the path unobstructed. The essential point is that this decision is made times after times the photon has already navigated the double slits and is well on its way to the detector. According to our classical understanding of the world, a photon's history should be fixed once it passes the slits. It either went through the left slit or the right one. That event is now in the past. It seems logical that a later choice about what to measure should have no ability to alter what has already occurred. The past, we assume, is the past. However, This is not what the actual experiments reveal. The results are startling and directly contradict our intuition. If you choose to insert the witch path detector, the interference pattern completely disappears. It is as if each photon behaved like a solid particle, going through one slit or the other, producing just two bands on the screen. This happens even though your choice was made long after the photon passed the slits. If, however, you choose times not times to insert the detector, the classic interference pattern emerges, with multiple bands indicating that each photon behaved like a wave and passed through both slits simultaneously. Your decision, made in the present, appears to determine how the photon behaved in the past. This outcome seems to suggest that the future can influence the past. It is as though your future choice reaches backward in time, dictating the photon's past journey. Such a conclusion is deeply unsettling to our fundamental intuitions about causality. We expect causes to precede their effects, with the past shaping the future, not the other way around. How can an event be determined by something that has not happened yet? Most physicists, however, do not interpret the delayed choice experiment as evidence of backward causation. Instead, they propose a far stranger explanation. Until a photon is actually detected, it simply does not possess a definite history. The photon's path through the slits, and indeed its entire trajectory from the source to the detector, remains fundamentally undefined until a measurement forces it into a concrete state. History, in this view, is not fixed until it is observed. The past remains as indeterminate as the future until an interaction makes it real. If this interpretation leaves you feeling uneasy, you are in excellent company. It deeply troubled Albert Einstein as well. This line of inquiry leads us directly to what is arguably the most bizarre phenomenon in all of quantum mechanics, something Einstein famously dismissed as spooky action at a distance. For instance, it is possible to generate pairs of photons that are entangled, which means their properties are linked in a way that no classical mechanism can explain. The correlations between them are stronger than any theory of local hidden variables could ever produce. This entanglement seems to require some kind of instantaneous connection between the particles, regardless of how far apart they are separated. The process of entanglement works by creating two photons simultaneously through specific physical processes that link their quantum states. For instance, it is possible to create two photons whose polarizations are entangled. Polarization is a property related to the orientation of a photon's oscillating electromagnetic field, which can be vertical, horizontal, or any angle in between. For these entangled photons, if you measure the polarization of one and find it to be vertical, you will instantly know that its partner's polarization will be measured as horizontal when it is eventually checked. If you measure the first as having a diagonal polarization, the other will be found to be anti-diagonal. Their respective outcomes are perfectly and oppositely correlated. But here is where the true strangeness lies. Before any measurement is made, neither photon possesses a definite polarization at all. Each one exists in a superposition of all possible polarizations simultaneously. It is only at the moment you measure one of them that both photons instantly collapse into definite correlated states. This collapse occurs instantaneously, no matter how vast the distance separating the two photons. Imagine sending one entangled photon to a laboratory on Earth and its partner to a laboratory on Mars. When the scientist on Earth measures their photon and gets a result, the photon on Mars, millions of miles away, instantaneously acquires the corresponding property. No signal could possibly travel between them fast enough to communicate the information, as it would have to exceed the speed of light. The correlation simply appears, immediately and without delay. Einstein found this concept abhorrent. He spent the latter part of his career arguing that quantum mechanics must be an incomplete theory. He insisted that there must be some deeper, more fundamental theory involving hidden variables that would explain these correlations without resorting to such spooky, instantaneous connections across the cosmos. Einstein remained certain that photons possessed definite polarizations from the moment of their creation, suggesting that quantum mechanics was merely incomplete because it couldn't describe these hidden variables. Then, in 1964, a profound breakthrough came from physicist John Bell. He demonstrated mathematically that Einstein's hidden variable theories would yield different predictions from quantum mechanics under specific experimental conditions. While the difference was subtle, it was crucially measurable. If Einstein's view held, the correlations between entangled photons would be constrained by a set of mathematical rules, now known as Bell inequalities. But if quantum mechanics was correct, and properties were not definite until measured, these inequalities could be violated. The debate could finally be settled by experiment. When those tests were conducted, beginning with Alain Aspect's pioneering work in the early 1980s and continuing with increasing precision, the verdict was clear. Quantum mechanics was vindicated. The observed correlations defy Bell's inequalities, matching exactly what quantum theory predicts and what no local hidden variable theory can explain. In 2022, Aspect, along with John Clauser and Anton Zeilinger, received the Nobel Prize in Physics for experimentally proving the violation of Bell inequalities and confirming the reality of quantum entanglement. The strangeness Einstein could not accept was now an established fact. This confirmation, however, does not mean entanglement allows for sending messages faster than light. When an observer measures their photon, the result they get is fundamentally random. There is no way to control the outcome. Because of this randomness, no information can be encoded. The remarkable correlation between the entangled particles only becomes evident when the two distant observers compare their measurements. That comparison must rely on classical communication, which is itself bound by the speed of light. Yet, entanglement does reveal that quantum mechanics is non-local in a profound sense. Two entangled photons, regardless of the distance separating them, behave as a single, unified quantum state. A measurement performed on one instantaneously influences the potential outcome of a measurement on the other. This spooky action doesn't violate relativity, as no useful information is transmitted faster than light, but it does force us to confront a reality that is deeply interconnected in ways our classical intuition simply cannot accommodate. So, after all this, what is a photon? It is perhaps easier to start by defining what it is not. A photon is not a tiny, solid ball of light moving through space along a fixed and predictable trajectory, like a miniature bullet fired from a gun. The classic double-slit experiment provides definitive proof of this. If photons were simple particles, they could not possibly interfere with themselves to create the distinct patterns of light and dark that are consistently observed. At the same time, a photon is also not a classical wave, spreading continuously through space with a defined amplitude at every point. The photoelectric effect is the key experiment that rules out this description. If light were a classical wave, its energy would be linked to its intensity, not its frequency, and electrons would be liberated from a material gradually rather than instantly. The experimental evidence thus rules out the classical wave model just as decisively as it rules out the classical particle model. This leaves us with a new category of existence. The photon is a quantum object, something that transcends our familiar classical divisions of wave and particle. It is best described by a wave function, a mathematical construct that defines probabilities instead of certainties. This wave function propagates through space, interfering with itself and demonstrating all the characteristics of a wave. Yet, the moment the photon interacts with a detector, the moment it is measured, the wave function collapses to a single point. In that instant, the photon appears at a specific location, exhibiting the discrete properties of a particle. This means that before it is measured, a photon does not have a definite position. It does not travel along one specific path from its source to the detector. In a way that challenges visualization, it seems to explore all possible paths at once. These potential pathways interfere with one another on a quantum level, and this interference pattern dictates the probability of where the photon might be found. However, only the final outcome, the detection of the photon, is definite. Everything that comes before that moment exists only as a cloud of possibility. This concept is profoundly counterintuitive. We are accustomed to a world where objects possess definite properties, whether we are observing them or not. A rock in a field has a precise location, even when no one is looking at it. The rock does not dissolve into a haze of probability, only to coalesce into a solid object when an observer appears. Our everyday experience suggests that objects simply exist, with their properties independent of measurement. But photons, electrons, and all other quantum objects behave differently. Their properties are genuinely undefined until a measurement brings them into being. The act of measurement does not simply reveal a pre-existing quality. It actually creates that quality. Before the measurement, the property, in any definite sense, does not exist. This bizarre feature of reality has created a deep philosophical divide among physicists. Some are comfortable with this picture, accepting that this is simply how the universe operates at its most fundamental level. From this perspective, our intuitions, which evolved to navigate a macroscopic world of rocks, trees, and predators, are ill-equipped for the quantum realm. They argue that we should update our understanding of reality rather than demanding that the universe conform to our classical expectations. Others, however, find this conclusion deeply unsatisfying. They continue to search for alternative interpretations of quantum mechanics, hoping to find a model that preserves some notion of an underlying objective reality, where things have definite properties even when they are not being observed. One of the most prominent of these alternatives is the many worlds interpretation, first developed by Hugh Everett in the 1950s. This theory proposes that the wave function never actually collapses at all. Instead, every time a quantum measurement is performed, the entire universe splits into multiple branches. Each branch corresponds to one of the different possible outcomes. In one branch of reality, the photon passed through the left slit. In another, completely separate branch, it passed through the right. According to this interpretation, both outcomes truly occur, but they do so in parallel universes that can no longer interact with one another. While we only perceive a single reality, some theories suggest this is just one branch among many, with all possible outcomes unfolding somewhere in a vast multiverse. An alternative perspective, known as the pilot wave interpretation, or Bohmian mechanics, named for physicist David Bohm, offers a different picture. It posits that particles always have definite positions. Their movements are simply guided by a subtle wave that permeates space, dictating their path. In this view, a photon doesn't mysteriously pass through two slits at once. It follows a distinct trajectory through one or the other. However, its guiding wave travels through both slits, creating the interference pattern by steering the particles towards certain regions and away from others. What is particularly fascinating is that these alternative interpretations yield predictions identical to those of standard quantum mechanics for every experiment conducted to date. With current technology, they are not experimentally distinguishable from one another. The choice between them often comes down to philosophical preference, a search for a depiction of reality that feels more intuitive rather than a matter of scientific necessity. The fact that this debate has persisted for nearly a century since quantum mechanics was formalized underscores just how deeply unsettling the photon's true nature remains. One conclusion is inescapable. The photon is not a simple particle, nor is it a simple wave. It is a quantum entity that fundamentally defies such classical categorization. It displays wave-like characteristics as it propagates through space, yet exhibits particle-like behavior when it interacts with matter. To truly grasp its identity, both aspects are essential. Neither one alone provides a complete description. Any attempt to confine the photon to a single category invariably results in contradictions and paradoxes. This wave-particle duality is not a feature unique to photons. It is a truly fundamental principle that applies to all quantum objects. Electrons, protons, neutrons, and even entire atoms demonstrate both wave and particle properties, depending on the method of measurement. In 1923, French physicist Louis de Broglie theorized that all matter possesses wave properties, with a wavelength inversely proportional to its momentum. This means that heavy, fast-moving objects have wavelengths that are too minuscule to detect. In contrast, light, slow-moving particles have longer, measurable wavelengths. This remarkable prediction was experimentally verified in 1927, when Clinton Davison and Lester Germer observed electron diffraction. By firing electrons at a crystal surface, they saw an interference pattern, exactly what one would expect from waves diffracting off a regular atomic structure. Today, the wave nature of matter is a well-established principle, routinely applied in technologies like electron microscopes, which can achieve resolutions far beyond the limits of traditional light microscopy. Yet, photons hold a unique place in the history of science as the first quantum objects to be identified. It was light that first refused to conform to the established categories of classical physics, demanding a radically new framework for understanding reality. Because light is so easy to generate, control, and observe, photons continue to be the perfect system for investigating quantum phenomena. It is no exaggeration to say that a very significant portion of our knowledge about quantum mechanics was first discovered through the study of photons, with many of the classic experiments that expose quantum strangeness relying on light. The quantum characteristics of photons also have profound practical applications that influence our daily lives. Lasers, for instance, are entirely dependent on these properties. The light from a laser is coherent, which means all its photons exist in the identical quantum state, oscillating perfectly in phase with one another. This level of coherence is impossible to attain with classical light sources, and is the enabling principle behind everything from barcode scanners and fiber optic communications to highly precise surgical operations. Quantum cryptography leverages a different quantum principle, the fact that measuring a quantum system inevitably alters it. This allows for the creation of communication channels that are fundamentally impervious to eavesdropping. If an unauthorized party attempts to intercept the photons that carry a quantum encrypted message, their actions will disturb the photon's quantum states in a way that is immediately detectable. In essence, any attempt to listen in announces itself. The very laws of physics themselves provide a security guarantee that no classical encryption method can ever hope to match. Quantum computing, meanwhile, harnesses the principles of superposition and entanglement to execute certain calculations at speeds exponentially greater than any classical computer. A classical bit of information is binary, existing as either a 0 or a 1. A quantum bit, or qubit, however, can exist in a superposition of both 0 and 1 simultaneously. This extraordinary property enables quantum computers to explore a vast number of possibilities in parallel. Photons are among the leading candidates for creating qubit hardware, as they are relatively easy to manipulate, can maintain their quantum states for extended periods, and can be transmitted over long distances using existing optical fibers. But even with this impressive array of transformative applications, the fundamental mystery persists. What is a photon, really? This question goes beyond what it does, how we describe it with mathematics, or what we can build with it. It probes its very essence. What kind of entity can exist in a superposition of states? What kind of object possesses no definite properties until it is measured? What is the nature of the reality that the wave function describes? For a century, these questions have captivated the world's greatest scientific minds, and they remain profoundly unanswered. The photon, this seemingly simple packet of light, holds mysteries we have not yet managed to solve. We can calculate its behavior with astonishing accuracy and predict the outcomes of experiments to 10 decimal places, yet we are still in the dark about what a photon truly is. Perhaps the issue is not a failing of physics, but a limitation of human intuition. Our brains evolved to navigate a macroscopic world, to track animals, evade dangers, and remember the locations of resources. We did not evolve with the capacity to visualize quantum phenomena. It could be that the quantum realm is simply and inherently unvisualizable, a domain that lies forever beyond the grasp of our imagination and is accessible only through the abstract language of mathematics. Then again, perhaps future breakthroughs will grant us a new level of understanding. It is possible that a physicist, not yet born, will devise a way to interpret quantum mechanics that finally satisfies our innate desire for a comprehensible reality. The wave function might describe something genuinely tangible that we simply have not yet learned how to perceive. For the time being, we must coexist with this mystery. The photon is real. It behaves in ways we can describe with precision and predict with accuracy. But what it is, in and of itself, remains one of the most profound questions in all of science. And that enigma extends into an even stranger territory, one where photons experience a concept we take for granted, time itself, in a way that is radically different from our own. The photon's bizarre quantum properties are just one layer of its mystery. A deeper strangeness emerges not from quantum theory, but from Albert Einstein's special theory of relativity. In 1905, the same year he introduced light quanta, Einstein laid the groundwork for a radical view of how photons interact with space and time. But even this phrasing is deceptive, as it implies photons experience reality in a way similar to our own. The startling truth is that, from a photon's perspective, time may not exist at all. What does it even mean to exist without the passage of time? To grasp the depth of this claim, we must first look at the ideas Einstein overturned. For centuries, the scientific consensus, guided by Isaac Newton, treated space and time as absolute constants. Space was envisioned as a fixed, unmoving backdrop for all events, while time was thought to be a single master clock for the cosmos, ticking uniformly for everyone, everywhere. This framework was the bedrock of Newtonian mechanics, a system that successfully described everything from cannonballs to planets for over 200 years. The universe, in this view, was a predictable, clockwork machine. But the very success of this model may have hidden a more complex reality. Einstein's theory of special relativity completely dismantled this classical picture. It rests upon two core postulates that, while seemingly straightforward individually, produce revolutionary results when taken together. The first, known as the principle of relativity, asserts that the laws of physics are identical for any observer in uniform motion. This concept, first articulated by Galileo, feels intuitive. Inside a smoothly moving train, for example, physics behaves exactly as if you were stationary. No internal experiment can reveal your motion. The true revolution, however, begins when this familiar idea is combined with Einstein's second principle. The second principle is where relativity departs sharply from common sense, and its consequences are far-reaching. It declares that the speed of light in a vacuum is absolute. It is constant for all observers, no matter their own motion or the motion of the light source. In the emptiness of space, light travels at precisely 299,792 kilometers per second. This isn't an approximation, it is an unyielding cosmic speed limit. This value is so fundamental to the fabric of our universe that it is designated by its own symbol, c, from the Latin word times celeritas, meaning swiftness. The existence of such an absolute constant raises a profound question about the nature of reality itself. On its face, this principle seems impossible, even absurd. It directly contradicts our daily experience with how speeds should combine. For example, if you are standing on a platform as a train goes by at 100 kilometers per hour, and someone on that train throws a ball forward at 20 kilometers per hour relative to the train, you would observe the ball moving at 120 kilometers per hour. The velocities simply add together. This is the straightforward arithmetic of motion that governs our world, a rule that seems like unshakable common sense. Now, let's apply that same logic to light. Suppose a friend in a spaceship is traveling in the same direction as a photon at half the speed of light. Logic dictates that from your friend's vantage point, the photon should only seem to be moving at half of its normal speed. This is how all other objects in the universe behave. Yet, light is the exception. Regardless of the friend's speed or direction, they will measure that photon passing them at the exact same speed, c. Whether they race toward the light source, away from it, or alongside it at 99% of light speed, the photon will still zip past them at times c, not at some reduced relative velocity. Nature, it seems, has a different set of rules for light. The speed of light, therefore, is absolute constant for every observer in every situation. This wasn't just a theoretical postulate. It was an established experimental fact even before Einstein formulated his theory. The most famous confirmation came from the Michelson-Morley experiment in 1887. This experiment was designed to detect the luminiferous ether, a hypothetical medium thought to carry light waves, by measuring variations in the speed of light as the Earth moved through it. The result was a stunning failure. They found no difference at all. Light's speed was identical in all directions. For nearly 2 decades, this null result was a deep puzzle for physics, a mystery that awaited Einstein's revolutionary explanation. Einstein's genius was to invert the problem. He realized that if the speed of light is truly constant for everyone, then something else must be variable. That something was space and time itself. He proposed that space and time are not the fixed, absolute backdrops Newton had envisioned. Instead, they are dynamic and malleable, capable of stretching and compressing. For different observers in motion, space and time must adjust themselves in just the right way to ensure that every single measurement of light's speed yields the same value, c. This was a monumental shift in thinking, suggesting that the stage of reality changes for each actor. This radical concept leads directly to some of the most famous predictions of special relativity, time dilation and length contraction. It is crucial to understand that these are not mere optical illusions or artifacts of measurement. They are real, physical phenomena woven into the very fabric of space-time. Time dilation, for instance, dictates that time itself passes at different rates for observers who are moving relative to one another. If you were to travel at a high velocity relative to me, I would observe your clock ticking more slowly than my own. From my perspective, your heart would beat slower and your biological processes would decelerate. The strangest part of this phenomenon is its perfect symmetry. From your moving perspective, you would observe nothing unusual about your own time. Instead, you would see times my time's clock as the one running slow, because from your point of view, I am the one in motion. This is not a paradox. It is a direct consequence of the first principle of relativity. There is no privileged absolute frame of reference. Neither of us can claim to be truly at rest. Both viewpoints are equally valid, revealing a universe where the flow of time is relative to the observer. The degree of this time dilation is not arbitrary. It is governed by a precise mathematical formula derived directly from the constancy of light speed, and the effect is proportional to the relative velocity. In our daily lives, these effects are imperceptible. For a passenger on a jetliner traveling at 1,000 kilometers per hour, time slows down by only a few nanoseconds over the course of an entire flight. This explains why Newtonian physics works so well for our everyday world, but it also shows that a deeper, stranger reality is always present, just beneath the surface of our perception. To detect this effect requires atomic clocks of extraordinary precision, and such experiments have confirmed the predictions exactly. But as speeds approach that of light, the phenomenon of time dilation becomes dramatic. At 90% of light speed, time's passage slows to just 44% of its normal rate, meaning a clock moving this fast would tick less than half as often as one at rest. If that speed increases to 99% of light speed, time flows at only 14% of its usual pace, at 9%, it slows to a mere 4.5%. The faster you travel through space, the slower you travel through time, a principle repeatedly verified with high-energy particles. A remarkable confirmation comes from muons, subatomic particles created when cosmic rays strike the upper atmosphere. At rest, muons have an extremely short lifetime of about 2.2 microseconds. Given their altitude and speed, they should decay long before ever reaching the Earth's surface. Yet, because muons travel at nearly the speed of light, time passes much more slowly for them from our perspective. From their own point of view, they live out their normal, fleeting existence. From our stationary viewpoint, however, their lives are extended, allowing them to reach ground-based detectors in large numbers. The muon experiment shows that time dilation is not just theory, but a measurable fact of nature. This principle has practical applications in our daily lives, most notably with GPS satellites. Orbiting the Earth at high velocities, their onboard clocks run slightly slower than clocks on the ground. Without adjustments, this effect from their orbital speed would cause a drift of about 7 microseconds every day. This seemingly tiny discrepancy would introduce positioning errors of several kilometers, rendering the system useless. The fact that your smartphone can pinpoint your location within a few meters is a daily, functional testament to Einstein's theory. The spatial counterpart to time dilation is a phenomenon known as length contraction. This principle states that objects appear shorter along their direction of motion. If a spaceship were to fly past you at 90% of the speed of light, it would look physically compressed, shorter than it would be if stationary. For the crew aboard the vessel, however, its dimensions would seem perfectly normal. Instead, it would be your measuring instruments that appear compressed to them. Both perspectives are equally valid within their own frames of reference, revealing a universe where there is no absolute length, just as there is no absolute time. This leads to a pivotal question about the very nature of light. What happens at the speed of light itself? The formula for time dilation is governed by the Lorentz factor, named for the Dutch physicist Hendrik Lorentz. This factor is directly dependent on velocity, and as that velocity gets closer to c, the Lorentz factor grows toward infinity. Consequently, time dilation would become infinite. For any object traveling at the precise speed of light, this suggests that time would stop completely. This conclusion presents a paradox. Can anything actually travel at the speed of light? For objects that possess mass, the answer is no. As any massive object accelerates, its kinetic energy increases. Near the speed of light, this energy requirement skyrockets. To accelerate an object with mass to exactly the speed of light would demand an infinite amount of energy, a clear impossibility. This is why you, spaceships, and planets can never reach the speed of light. We can only get infinitesimally close, reaching 99.99% of that ultimate limit, but never crossing it. The speed of light is a fundamental barrier for all matter. Photons, however, are fundamentally different because they possess no mass precisely zero. This single property changes everything. Photons do not need to be accelerated from a slower speed. In fact, they cannot exist at any other speed. From the instant they are created to the moment they are absorbed, photons travel at exactly the speed of light, c. They are born at c, they journey at c, and they are destroyed at c. The speed of light is not a goal for a photon. It is the defining characteristic of its existence. This reality leads to a profound and almost incomprehensible consequence. From the photon's own perspective, no time passes, ever. A photon emitted from a star in a distant galaxy might travel across the cosmos for 10 billion years before it strikes a telescope on Earth. Yet, for that photon, this immense journey has no duration whatsoever. If we can speak of a photon's frame of reference, the moment of its emission and the moment of its absorption are simultaneous. The photon's entire existence, from creation to destruction, unfolds in a single, timeless moment of zero duration. To make this more concrete, consider a photon leaving the sunday. From our perspective on Earth, its journey takes about 8 minutes and 20 seconds. We can map its progress. After 1 minute, it is 18 million kilometers away. At 4 minutes, it is halfway here. The journey has a clear duration and unfolds through stages. But from the photon's point of view, none of this intermediate travel exists. The instant it leaves the sun's surface is identical to the instant it strikes your retina. There is no gap, no journey, and no waiting. For the photon, departure and arrival are the same event. This also means that from the photon's perspective, distances contract to zero. At the speed of light, length contraction becomes absolute. The 93 million miles between the sun and Earth collapse to nothing. From the photon's point of view, the sun and your eye are not just close, they are at the exact same location in space. It's a startling idea, though physicists caution that speaking of a photon's frame of reference isn't strictly correct. The very laws of physics as we know them break down in such a construct, leaving us at the edge of what our analogies can describe. The mathematical framework of special relativity was developed for observers traveling slower than the speed of light. A critical issue arises when applying these equations directly to the speed of light, c, where the formulas break down, yielding undefined results like infinity from division by zero. Consequently, the statement that time stops for a photon is best understood as an extrapolation. It describes the theoretical limit as velocity approaches c, rather than a state the theory can formally describe. Even so, this mathematical boundary hints at the profound and unique nature of a photon's existence. As an object accelerates toward the speed of light, its experience of time slows dramatically relative to a stationary observer. The logical endpoint of this time dilation, at the absolute velocity c, is that the passage of time itself approaches zero. Photons exist precisely at this limit, on the very boundary of what is physically possible. This leads to some truly counterintuitive consequences. Consider the light from the Andromeda galaxy, located approximately 2.5 million light-years away. From our perspective on Earth, this journey takes millions of years. But from the photon's own frame of reference, no time has passed at all. The entire vast journey is instantaneous, making the photon, in a sense, eternally new. The cosmic microwave background offers an even more staggering example of this temporal disconnect. This faint radiation is the residual heat from the Big Bang, emitted when the universe was just 380,000 years old and first became transparent. For nearly 13.8 billion years, this ancient light has traveled across the expanding cosmos to reach us, representing the oldest observable signal from our universe's infancy. And yet, for the individual photons that carry this signal, no time has passed since their emission from that primordial plasma. Their departure from the dawn of time and their arrival in a modern telescope are, from their perspective, a single unified event. There is a profound quality to this realization. The very photons that deliver information about the earliest moments of cosmic history, from the ignition of the first stars to the light of the most distant galaxies, experience their entire existence in an instant. They function as perfect messengers from a distant past, completely unaware of their own message or the immense journey they have undertaken. Because they experience no passage of time, they can carry no memory of their travels. They simply exist at the timeless boundary between their point of emission and their point of absorption. This timeless nature of photons also connects in intriguing ways to their fundamental quantum properties. Within the framework of quantum field theory, the Feynman-Stueckelberg interpretation allows for antimatter to be mathematically described as its corresponding matter particle traveling backward in time. For instance, a positron, which is the antiparticle of an electron, can be viewed in the governing equations as an electron moving from the future into the past. This perspective challenges our intuitive sense of time's arrow. This interpretation becomes particularly elegant when applied to photons. A photon is a unique particle in that it is its own antiparticle. There is no distinct antiphoton with opposite properties. This special status aligns perfectly with the idea that photons experience no time. If, for a photon, there is no meaningful temporal direction, if the past and future are collapsed into a single, indivisible instant, then the distinction between moving forward and backward in time becomes entirely meaningless. It follows logically that a particle that does not experience time cannot be distinguished from its own time-reversed self. This raises another fundamental question. Why does light travel at this specific speed of 299,792 kilometers per second? The answer is one of the most profound discoveries in all of physics. The speed of light isn't fundamentally about light itself. Rather, it is a built-in, non-negotiable property of space-time. This universal constant, c, represents the maximum speed at which information and causal influence can propagate through the universe. In essence, it acts as the conversion factor between space and time, revealing them to be two facets of a single, underlying reality called space-time. In fact, even in a hypothetical universe containing no light or electromagnetic fields, this ultimate velocity would still exist as a fundamental cosmic speed limit. It is the speed at which any massless entity must travel. For example, gravitational waves, ripples in the fabric of space-time itself, first detected in 2015, also propagate at exactly c. When James Clerk Maxwell formulated his equations of electromagnetism, he discovered they predicted waves moving at a speed determined by fundamental constants of free space. He calculated this speed and found it matched the measured velocity of light, but he had simply uncovered a speed already woven into the very fabric of the cosmos. But why must there be a maximum speed at all? The reason appears to be rooted in the deep principles of causality and the logical coherence of the universe itself. If there were no universal speed limit, the inviolable relationship between cause and effect could shatter. It would theoretically become possible to send information into one's own past, creating irresolvable paradoxes. One could, for instance, send a message back in time with instructions not to send the message in the first place, a logical contradiction that would render reality incoherent. The existence of this maximum speed, combined with the other principles of relativity, works to preserve a consistent causal structure for all observers. It ensures that while individuals may disagree on the timing or duration of events, they will all agree on the fundamental sequence of cause and effect. A photon, by traveling at this absolute maximum velocity, exists on the very edge of this causal structure. It moves along what physicists describe as a light cone, the boundary that separates events that can be influenced from those that cannot, defining the absolute limit of connection in our universe. In physics, the line between events that can affect one another and those that cannot is sharply and elegantly defined. This critical boundary can be visualized with a space-time diagram, where time flows vertically and space stretches horizontally. Imagine your present self positioned at the origin, the here and now. From this point, your entire past unfolds below, while all possible futures lie above. From your position, two lines extend outwards at 4-5 degree angles, tracing the path of light departing from you. These lines form a future light cone, and anything inside it can be affected by your actions. Similarly, two lines extending downward form a past light cone. Any event within this cone could have influenced you, as a signal had enough time to reach you, moving at or below the speed of light. This model provides a clear map of cosmic cause and effect. But what about the vast regions of space-time that lie outside both cones? Events there are said to exist in elsewhere. They are causally disconnected from you, happening too far away in space and too recently in time for any signal to bridge the gap. Photons, traveling precisely at light speed, trace the very edges of these light cones. In doing so, they literally define the structure of causality, drawing the scaffold that separates the interconnected parts of the universe from those that are forever isolated from our present moment. This fundamental role as the arbiter of causality points to another of the photon's peculiar properties, one that forms a crucial bridge between its relativistic nature and its quantum identity. Because photons travel at the universe's absolute speed limit, a constant known as c, they are necessarily massless. According to relativity, this also means they experience no passage of time from their own perspective. A profound consequence of this timeless, instantaneous journey is that a photon of a given frequency is an identical object, no matter how an observer is moving relative to it. This simple fact raises a deep philosophical question about what constitutes the true nature of a particle versus our limited, relative perception of it. For instance, a photon of green light with a specific wavelength of 500 nanometers is the same essential particle, whether it is observed from a stationary laboratory or from a spaceship traveling at 99% of the speed of light. An observer's motion does, however, alter the photon's times apparent times characteristics. If you move toward a light source, its light appears blue-shifted to a higher frequency. If you move away, it appears red-shifted to a lower frequency. This is the well-known Doppler effect, extended from sound to light. Yet, it's crucial to understand that the photon itself has not changed. What has changed is the relationship between the photon and the observer. This stands in stark contrast to particles with mass, like an electron. A fast-moving electron is genuinely, measurably different from a slow one. Its kinetic energy and its de Broglie wavelength are distinct. One cannot speed up or slow down a photon. It always travels at exactly c, and we can only change our frame of reference relative to it, altering its appearance, but not its fundamental being. This absolute constancy of the photon has powerful implications for cosmology, allowing these particles to act as perfect messengers from the distant past. A prime example is the cosmic microwave background, or CMB. This ancient light is effectively a snapshot of the universe when it was just 380,000 years old. Before this time, the cosmos was an opaque, hot plasma. But at this specific epoch, it cooled sufficiently for neutral atoms to form, a moment which made the universe transparent to light for the first time. The radiation released then was mostly in the visible spectrum, with a thermal signature corresponding to a temperature of about 3000 degrees Kelvin, similar to the reddish glow of a relatively cool star. In the 13.8 billion years since that formative era, the universe has expanded by an incredible factor of roughly 1,100. As the fabric of space itself stretched, it elongated the wavelengths of the photons traveling through it. Those original photons from the CMB have been stretched by this same factor. As a result, what was once visible light has been redshifted all the way into the microwave portion of the spectrum, with wavelengths now measured in millimeters. The radiation's apparent temperature has correspondingly dropped from 3000 Kelvin to just 2.7 Kelvin, a mere whisper above absolute zero. And yet, these are the very same photons. Their intrinsic nature is completely unchanged. They still travel at light speed, experience no time, and carry with them an unspoiled record of their creation. It is as if the universe has simply grown around these timeless relics. The intricate relationship between quantum mechanics and special relativity, which together describe the photon's dual existence as both a particle and a wave traveling at a fixed speed, remains one of the deepest and most challenging subjects in all of physics. Our most successful description is a framework known as quantum field theory, or QFT. In this powerful model, a photon is understood not as a simple particle, but as a localized excitation, a quantum ripple in the electromagnetic field that permeates all of spacetime. While this theory is incredibly accurate, it does not represent the final word, as profound puzzles remain. The greatest of these puzzles lies at the intersection of quantum theory and our modern understanding of gravity. That understanding is Einstein's theory of general relativity, a masterwork he completed in 1915. It reimagines gravity not as an invisible force, but as a direct consequence of the curvature of space-time. Massive objects, like stars and planets, bend and warp this four-dimensional fabric around them. Other bodies then simply follow the straightest available paths called geodesics through the distorted geometry, an effect we perceive as gravitational attraction. This is why planets orbit the Sun. Remarkably, photons are also bound by these rules. Despite being massless, they too must follow the curved pathways laid out in space-time. This principle explains the observable phenomenon of gravitational lensing, where light from distant stars and galaxies is seen to bend as it passes by massive objects, faithfully tracing the contours of a warped universe. This phenomenon, known as gravitational lensing, received its first dramatic confirmation during a 1919 solar eclipse. The observation that the sun's immense mass could bend the light from distant stars, subtly altering their perceived positions near the solar disk, provided powerful validation for Einstein's theory and catapulted him to global fame. Today, this effect has become an indispensable tool for astronomers. The gravity of massive galaxy clusters acts as a cosmic lens, warping the light from even more remote galaxies situated behind them. This can result in multiple images of a single distant object, stretch its appearance into luminous arcs, or magnify it so intensely that otherwise invisible objects become detectable. The warping of space-time by mass influences photons just as it does all other forms of matter and energy. However, it is here that our scientific understanding reaches a critical limit, as we lack a complete quantum theory of gravity. We do not yet possess the language to describe how gravity and space-time operate at the quantum scale. While general relativity portrays gravity as a smooth, continuous geometry, quantum mechanics insists that reality is fundamentally granular, composed of discrete units, or quanta. Reconciling these two foundational pillars of modern physics remains one of the most profound and difficult unsolved challenges in all of science. When a solution is found, it could very well transform our conception of the photon. The very fabric of spacetime might be structured differently than we imagine, and photons, as our primary probes of that structure, could unveil properties we cannot currently predict. For the moment, however, the picture of the photon we do have is more than strange enough to warrant a lifetime of study. It is a massless quantum of the electromagnetic field, an entity that is simultaneously a particle and a wave. It is a traveler, moving at the absolute maximum velocity permitted by the structure of spacetime itself. The photon is a messenger capable of traversing billions of light years of cosmic distance without experiencing the passage of a single moment of time. It is also a fundamental arbiter of causality, tracing the boundaries of the light cones that separate what can be influenced from what must remain isolated. The photon seems to exist at the nexus of everything we find paradoxical. It resides at the boundary between particle and wave, and at the very edge of time, experiencing none of it. It defines the limits of cause and effect, linking events that are just barely able to interact. Ultimately, it sits at the boundary of our own comprehension, showing us that the universe is far more bizarre than our everyday intuition allows. And yet, for all its profound strangeness, the photon is also an intimate part of our existence. It is the very light that allows you to perceive these words. It is the warmth you feel on your skin, delivered from a star 93 million miles away. It is the faint glimmer of every star that populates the night sky. It is the invisible signal carrying conversations and data through fiber optic cables at the speed of light. This quantum entity, which experiences no time and defines the structure of reality, is not a distant abstraction. It is everywhere, always. But how does this fundamental particle fit into the complete tapestry of modern physics? How does it function as the carrier of one of nature's fundamental forces? Exploring these questions reveals that the photon lies at the very heart of reality itself. We have explored the photon's quantum character and its perplexing relationship with time. We have seen how it embodies both wave and particle characteristics, how it can interfere with its own path, and how it feels no duration while crossing unimaginable cosmic voids. We have touched on entanglement, where paired photons exhibit correlations that defy any classical explanation. Now, it is time to synthesize these ideas and examine how modern physics describes what a photon truly is at its deepest, most fundamental level. This journey leads us to quantum electrodynamics, or QED, the theory that explains how light and matter interact. QED is far more than just another theory in physics. It is widely considered the crown jewel of 20th century science. It provides a mathematical framework of such extraordinary precision and predictive capability that it stands as one of humanity's most significant intellectual triumphs. The theory was developed in the late 1940s, emerging from the work of three physicists who were, for the most part, working independently of one another. These pioneers were Richard Feynman and Julian Schwinger in the United States and Shinichiro Tomonaga in Japan. In a remarkable convergence of scientific thought, all three arrived at functionally identical versions of the theory using distinct mathematical pathways. Their shared 1965 Nobel Prize in Physics was a formal acknowledgement that QED marked a revolutionary advance in our understanding of the natural world. The accuracy of the predictions made by quantum electrodynamics is almost impossible to fully grasp. The theory's calculations match experimental results to an accuracy of better than 1 part in a trillion. To offer some perspective on this number, if you were to measure the distance from New York to Los Angeles with this degree of precision, your measurement would be accurate to within the width of a single human hair. No other scientific theory, in any field, has ever demonstrated such a perfect correspondence between prediction and observation. By this metric, QED can be rightfully called the most successful scientific theory ever conceived. Within the framework of QED, the photon assumes a role that is far more profound than simply being a particle of light. Here, the photon is revealed to be the carrier of the electromagnetic force itself. This means that every time two charged particles interact, whether attracting or repelling or exchanging energy and momentum, they accomplish this by exchanging photons. When one electron repels another, it is because they are effectively trading photons. One electron emits a photon, which is then absorbed by the other, and the momentum carried by that photon pushes the two particles apart. Similarly, when a proton attracts an electron, binding it into a hydrogen atom, that force is mediated by a constant exchange of photons. The entirety of electromagnetism, one of the four fundamental forces of nature, is conveyed by these particles. This concept might seem counterintuitive. When you rub a balloon on your hair and watch it stick to a wall, you do not perceive any photons flying between the two surfaces. When a powerful magnet pulls a piece of iron toward it, there is no visible beam of light connecting them. This raises an important question. If these photon exchanges are happening constantly, why are they invisible? The photons that mediate the electromagnetic force between everyday objects are not the same as the photons that our eyes can see. These force-carrying particles are referred to as virtual photons, and they are fundamentally distinct from the real photons that travel through space and register on our retinas. A real photon is an independent entity, a stable packet of energy that propagates through space from a source to a destination where it can be detected. The photons streaming from the sun that warm your skin are real photons. They were created in the sun's fiery atmosphere, journeyed across the solar system, and were finally absorbed by molecules in your body. The photons emitted by a reading lamp, which allow you to see this text, are also real photons. They are discrete packets that can be detected, counted, measured, and absorbed, making them tangible components of our observable world. Real photons are messengers, tasked with carrying energy and information from one location to another. Virtual photons, by contrast, play a different and more enigmatic role. They exist only as fleeting intermediaries during interactions between charged particles and can never be directly observed as independent entities. Rather than traveling freely through space, they seem to spring into existence when one particle is disturbed, carrying that influence to another particle before they disappear. Their entire existence is just a transient flicker, governed by the Heisenberg uncertainty principle, which confines them to timescales so brief they can never be isolated. This description might sound like a mere mathematical abstraction, a computational tool instead of a physical truth. In a certain sense, whether they are real is a matter of philosophical interpretation. It is impossible, for example, to capture a virtual photon in order to study it. They only ever appear in the intermediate stages of a calculation, never as a final, observable result. And yet, without accounting for these virtual particles, the astoundingly accurate predictions of quantum electrodynamics, or QED, would completely fail. While their ultimate metaphysical status remains a subject of ongoing debate, their effects are undeniably real and have been measured with incredible precision. The physicist Richard Feynman devised a brilliant method for visualizing and calculating these complex quantum interactions. He introduced simple drawings, now universally known as Feynman diagrams, which have since become iconic symbols of modern physics. It is crucial to understand that these diagrams are far more than just mere illustrations. They actually represent a rigorous mathematical shorthand, a visual language that encodes the precise rules for calculating the outcome of particle collisions. In this particular system, matter particles like electrons are depicted as straight lines with arrows indicating their journey through time, while photons are represented by wavy lines. When two electrons interact, for instance, a Feynman diagram shows them as two straight lines approaching from the past. They are connected by a wavy line, the virtual photon, and then they separate, moving off toward the future. This exchanged photon carries momentum and energy from one electron to the other, causing them to alter their paths in an interaction that we observe as repulsion. This simple diagram, showing the exchange of a single photon, is only the beginning. QED reveals that more complex events are also possible, and it is here that the theory becomes both mathematically formidable and physically profound. For example, Before the exchanged photon reaches the second electron, its energy might momentarily manifest as an electron-positron pair, a particle and its antiparticle, which then annihilate each other, reforming the photon that continues on its journey. Alternatively, the photon itself might emit and reabsorb another virtual photon, or the electrons could emit and reabsorb their own virtual photons before or after the main exchange. These additional processes are visualized as extra loops and lines within the Feynman diagrams, and the possibilities are quite literally endless. For any given interaction, an electron might exchange 1, 2, or even 3 photons with its neighbor. Each of those photons could temporarily spawn an electron-positron pair, and each electron could be emitting and reabsorbing its own cloud of virtual photons. This raises a critical question. If there are infinite possible scenarios, how can the theory ever produce a finite, meaningful answer? Fortunately, not all diagrams carry the same weight. The complexity of a diagram is inversely related to its contribution. Simpler diagrams with fewer loops represent the dominant effects, while more intricate diagrams add only minor corrections. The contributions from extremely complex diagrams become so vanishingly small that they can be safely disregarded for almost all practical calculations. Even so, calculating all of these contributions, including just the most significant ones, was a monumental task for 20th century physics. The mathematics involved can be extraordinarily difficult, and early attempts to compute even basic processes yielded infinite values. These nonsensical results were a clear signal that something was deeply wrong with the theory. The critical breakthrough came when Richard Feynman, Julian Schwinger, and Shinichiro Tominaga each independently developed techniques to manage these infinities in a process known as renormalization. While the details are highly technical, the core insight was that certain infinite quantities could be systematically absorbed into the definitions of physical constants, such as the mass and charge of an electron. This clever, if at the time controversial, procedure was the key that unlocked the theory's predictive power. Once properly applied, the remaining calculations produced finite, sensible, and unbelievably accurate predictions. The magnetic moment of the electron stands as the most celebrated example of QED's remarkable precision. An electron behaves like a tiny spinning magnet, and the strength of this magnetism is described by a number known as the G factor. Basic quantum mechanics predicts that this G factor should be exactly 2. However, QED refines this picture, predicting small corrections that arise from the constant swarm of virtual photons and virtual electron-positron pairs that surround the electron. Calculating these corrections is an immense undertaking, requiring the evaluation of thousands of Feynman diagrams. When this is done, the result is a prediction for the electron's G factor that has been calculated to 12 decimal places. In one of the most stunning achievements in the history of science, this theoretical number matches the experimentally measured value perfectly to every single decimal place that we are currently able to measure. With this framework in mind, we can return to the question, what exactly is a photon? According to QED, a photon is an excitation of the electromagnetic field. This field is understood to permeate the entirety of space. At every point in the cosmos, there exists a value for the electric and magnetic fields, which were unified into a single electromagnetic field by James Clerk Maxwell in the 1860s. In the world of classical physics, these fields are treated as smooth and continuous, capable of holding any value and varying seamlessly from one point or moment to the next. But a fundamental principle of quantum mechanics is that nature is quantized. Energy is delivered in discrete packets, and angular momentum comes in distinct units. As it turns out, fields are quantized as well. This means that, at the most fundamental level, the electromagnetic field is not a smooth, continuous entity. Instead, It is composed of discrete quanta indivisible packets of excitation. Each single quantum of the electromagnetic field is what we identify as a photon. An analogy can help to clarify this abstract idea. Imagine a perfectly still pond, its surface representing the electromagnetic field in its lowest energy state or ground state. This simple image helps us grasp the profound concept of a quantum field at rest, a silent potential filling all of space, waiting for an energetic event to cause a ripple, a photon, to travel across it. Imagine a perfectly still pond, its surface extending from one shore to another. This is analogous to the vacuum state in quantum field theory, a field existing everywhere, but with nothing happening. No photons are present, and no disturbances are propagating. Now, picture a disturbance, like a stone dropped into the water. Ripples spread outward, each one a discrete excitation carrying energy, with its own wavelength and frequency. These ripples are like photons, and this field-based perspective helps explain some of the most counterintuitive aspects of the quantum world. In quantum field theory, the electromagnetic field is the pond, and photons are the waves that travel across it. When an atom is said to emit a photon, an electron has shifted to a lower energy state. The surplus energy is released not as a tiny projectile, but as an excitation within the electromagnetic field. This disturbance propagates outward at the speed of light. Conversely, when a photon is absorbed, that excitation reaches another electron, transferring its energy and causing the electron to jump to a higher state. The photon, as a distinct entity, therefore, exists only in the interval between its creation and its destruction. This field-centric view offers a powerful explanation for some of quantum mechanics' most perplexing behaviors. For instance, how can a single photon appear to pass through both slits in the famous double-slit experiment? The answer is that the photon is not a miniature billiard ball on a fixed trajectory. It is an excitation of a field that spreads through space like a wave. The field itself passes through both openings, creating an interference pattern on the other side. Only when this excitation interacts with a detector, when it is absorbed, does its energy manifest at a single, specific point. This elegant model resolves the apparent paradox of wave-particle duality by assigning each behavior to a different part of the photon's journey. This framework also sheds light on why a photon does not experience the passage of time. As an excitation moving at the maximum possible speed, the speed of light, it is subject to the full effects of special relativity. At this velocity, time dilation becomes infinite. From any reference frame we could possibly assign to the photon, its entire existence unfolds in a single, timeless instant. This concept challenges our everyday intuition, suggesting an existence unbound by the familiar progression of moments, where creation and absorption are a single event. Quantum electrodynamics, or QED, also provides an answer for why photons are massless, revealing deep connections within the theory's mathematical structure. In quantum field theory, mass is understood as the energy a field possesses even when it is at rest, with no excitations propagating. A massive particle, like an electron, is an excitation of a field that has this inherent rest energy, as described by Einstein's famous equation E equals mc squared. This energy is a fundamental property of the electron field itself. In contrast, a massless particle is an excitation of a field that has no rest energy at all. The electromagnetic field is one such field. There is no minimum energy threshold required to create a disturbance. This is why photons can possess any amount of energy, from the lowest energy radio wave to the most powerful gamma ray, and it is ultimately why they are massless. The masslessness of the photon has profound implications for the force it carries. Because photons have no mass, they can mediate the electromagnetic force over an infinite range. While the force between two charged particles weakens with distance, following an inverse square law, it never truly drops to zero. This means that, even across billions of light years, two charged particles continue to exert a subtle electromagnetic influence on each other, mediated by an exchange of virtual photons. This single property, zero mass, is what grants electromagnetism its cosmic dominion. This stands in stark contrast to the weak nuclear force, another of nature's fundamental interactions. The weak force governs certain forms of radioactive decay and is essential for nuclear fusion inside stars. It is mediated by particles known as the W and Z bosons. However, these bosons are extremely massive, weighing 80 to 90 times more than a proton. Because of their great mass, quantum uncertainty dictates that they can only exist for a vanishingly brief moment. During their fleeting existence, they can only travel a minuscule distance, about 0.1% of a proton's diameter. Beyond this subatomic range, the weak force is effectively non-existent. This comparison reveals a fundamental rule. A particle's mass determines the operational range of the force it carries. The photon's lack of mass is not an accident. It is intimately tied to a deep, underlying principle of the electromagnetic field known as gauge symmetry. This symmetry is one of the most critical concepts in modern physics, forming the foundation not only for electromagnetism, but for all fundamental forces. Gauge symmetry dictates that you can alter the mathematical description of the electromagnetic field in specific ways, such as shifting the phase of particle wave functions, without changing any physically measurable outcome. The resulting physics remains identical. The question this raises is profound. Why should a purely mathematical rule have such a powerful grip on physical reality? The most crucial implication of gauge symmetry is that it requires the force-carrying particle to be completely massless. If the photon possessed even the tiniest amount of mass, gauge symmetry would be broken, and the entire mathematical framework of electromagnetism would fall apart. This same principle holds true for the other fundamental forces. The gluons that mediate the strong nuclear force are also massless, which preserves the gauge symmetry of their theory, quantum chromodynamics. Likewise, the hypothetical graviton, the proposed carrier of gravity, must also be massless if it exists. In short, gauge symmetry and massless force carriers are inextricably linked. This, however, presents a significant puzzle. If gauge symmetry demands massless force carriers, how can the weak force be mediated by the massive W and Z bosons? This apparent contradiction drove a great deal of research in particle physics throughout the 1960s and 1970s. The resolution to this paradox involves a subtle but profound mechanism known as spontaneous symmetry breaking, which was theoretically developed by several physicists, including Peter Higgs, for whom the Higgs boson is named. The search for an answer to this question would lead to one of the greatest theoretical breakthroughs of the 20th century. In the phenomenon of spontaneous symmetry breaking, the fundamental equations governing a theory exhibit a certain symmetry that the system's lowest energy state fails to reflect. At the extreme energies of the early universe or within powerful particle accelerators, the weak force and electromagnetism are not distinct. They are fused into a single electroweak force. This unity is explicit, with the photon and the W and Z bosons all belonging to the same mathematical family as massless carriers of this unified force. However, a profound change occurred as the cosmos expanded and cooled. The Higgs field, which permeates all of space, settled into a non-zero value, triggering a symmetry-breaking event. This process endowed the W and Z bosons with mass, while the photon remained massless. The symmetry that once united them became hidden from view in our low-energy world, though it fundamentally persists within the underlying mathematical structure of the laws of physics. This event is the very reason we perceive electromagnetism and the weak force as separate phenomena in our world today. The photon's lack of mass preserves the infinite range of electromagnetism and its associated gauge symmetry in the low-energy universe we inhabit. In contrast, the massive W and Z bosons confine the weak force to incredibly short, subatomic distances, concealing the deeper unity. The photon, therefore, is far more than just a simple particle of light. It serves as a direct, observable window into the foundational structure of the Standard Model and the elegant symmetries that shape the entirety of physical law. Beyond its role in forces, the photon also reveals another deep truth about reality through entanglement. The non-local correlations observed between entangled photons, which Bell's theorem proves, cannot be explained by any local. Classical variables demonstrate that the quantum world is interconnected in ways that defy our everyday intuition. The theory of quantum electrodynamics, or QED, fully incorporates and predicts these correlations with astonishing precision, suggesting that entanglement is not an anomaly, but a natural outcome of how quantum fields operate. So, what exactly is a photon when we synthesize all this information? It is, first and foremost, an elementary particle, a fundamental constituent of nature as described by the Standard Model. It possesses zero mass and, as a consequence, travels perpetually at the speed of light. A photon carries energy that is proportional to its frequency and momentum derived from that energy. It also has an intrinsic angular momentum known as spin, with a value of 1 in the units used by physicists. This spin is what we observe as polarization, which can manifest in two states, such as left and right circular polarization. These properties are not just abstract labels, they are the core identifiers that define the photon's behavior in the universe. A photon is also understood as a quantum of the electromagnetic field, which is a discrete excitation of a field that extends throughout all of space-time. It's a subtle but crucial point. The electromagnetic field is not constructed from photons in the way a house is built from bricks. Instead, the field is the fundamental entity, existing everywhere, even in a perfect vacuum. Photons are the phenomena that occur when this field is excited above its lowest energy, or ground, state. They are localized disturbances, packets of energy and momentum that propagate through the field at the speed of light. In its role as the carrier of the electromagnetic force, the photon mediates every interaction involving electricity and magnetism, from the force that binds electrons to atomic nuclei, to the repulsion between two particles of like charge, to the radiation of heat from a warm object. All these processes are orchestrated by the exchange of photons. We can distinguish between real photons, which carry energy across space and can be detected, and virtual photons, which transmit forces between charged particles but cannot be directly observed themselves. They are the unseen messengers that make the structure of matter possible. Furthermore, a photon perfectly demonstrates wave-particle duality. In certain experiments, it behaves unmistakably like a wave, spreading out, interfering with itself, and diffracting around obstacles to create patterns that only waves can form. In other experimental setups, it acts as a discrete particle, striking a detector at a single point, delivering a quantized amount of energy, and registering as an individual click. Neither the wave nor the particle description alone is sufficient to capture the photon's true nature. Both are merely aspects of a more profound quantum reality that transcends our classical categories entirely. Perhaps most astonishingly, a photon experiences no passage of time. Because it travels at the universe's ultimate speed limit, it is subject to infinite time dilation. From its own perspective, a photon's entire existence, from the moment of its creation to the moment of its absorption, occurs in a single instant. Photons do not age or experience duration. A photon can cross billions of light years of cosmic expanse, yet for the photon itself, not a single moment passes. It exists at the very boundary of time as we know it. A photon can also become entangled with other particles, maintaining remarkable non-local connections over any conceivable distance that no classical mechanism can possibly explain. For these entangled photons, the very concept of spatial separation seems to lose its conventional meaning, profoundly challenging our deepest intuitions about how the universe ought to work on a fundamental level. All of these properties are profoundly strange. Each one defies the intuition we've built from our experience with macroscopic objects. Yet, every single one of these strange properties is rigorously supported by experiment and measurement, confirmed by the most precise observations humanity has ever made. The photon seems strange because, at its most fundamental level, nature itself is strange. Quantum reality does not conform to the expectations of brains that evolved to navigate the classical world. In this realm, particles lack definite properties until measured, and effects can be correlated across vast distances without any signal passing between them. The photon forces us to confront these uncomfortable truths because it is one of the simplest quantum systems, one of the easiest to produce, detect, and manipulate. It is one of the most thoroughly investigated entities in all of physics, and yet it remains in many ways deeply mysterious, constantly pushing the boundaries of our understanding. So, the next time you see light, whether it is the sunlight warming your face, a distant star twinkling in the night sky, or the glow from your screen, take a moment to consider what you are truly witnessing. You are seeing photons, the massless quanta of the electromagnetic field, individual entities traveling at the absolute maximum speed the universe allows. They are timeless messengers that traverse cosmic distances without experiencing a single moment, and they are the carriers of the force that holds atoms together, making all of chemistry and life possible. These strange entities, which are simultaneously waves and particles, carry information about the world to your eyes, where they are absorbed by molecules in your retina, triggering the electrical signals that your brain interprets as sight. When light enters your eye, photons trigger signals that journey along the optic nerve. In your brain, these signals are processed into vision. It's a remarkable thought that these same photons, governed by the strange rules of quantum mechanics and relativity, are the foundation of every visual memory you possess. Every face, every sunset, and every word on this page is brought to you by them. But what, fundamentally, is a photon? It is a messenger from the cosmos, carrying energy and information at the universe's ultimate speed limit. It is a quantum of the electromagnetic field, the basic medium for interactions between charged particles. It also serves as a window into the deepest structures of physics, hinting at symmetries and unifications we are only just beginning to grasp. For over a century, it has remained a puzzle that has challenged humanity's greatest minds, a mystery not yet entirely solved. Light itself seems so commonplace, constantly illuminating our world and enabling life to flourish. Yet, scrutinizing its true nature through experiments reveals something extraordinary. The discovery that light is composed of photons reveals some of the most bizarre phenomena in existence. Even Albert Einstein, who first proposed that light exists in these discrete packets, or quanta, spent the rest of his life troubled by the theory's implications. He could never fully embrace quantum mechanics, convinced a deeper, more sensible reality must lie beneath it, one that would restore determinism. Despite his intuition, experiments have repeatedly confirmed that quantum mechanics and its description of photons is correct. This raises a profound question about the limits of human intuition when confronted with the fundamental nature of reality. Perhaps future breakthroughs in physics will resolve these enduring mysteries. A successful theory of quantum gravity for instance, might reveal the photon to be an even stranger entity than we currently imagine. It is also possible our current theories are merely approximations of deeper truths we have not yet glimpsed. After all, the history of physics is filled with such surprises, and will likely surprise us again. For now, however, we are left with the photon as we understand it, a massless, timeless quantum particle that carries light across the cosmos. It is a paradox that this particle is both one of physics' best understood entities and yet profoundly mysterious. Both statements can be true at once, which is perhaps fitting for a particle that famously exists in a superposition of states. The photon offers a lesson in humility, showing us the universe operates on principles that often transcend our everyday intuition. It demonstrates that reality at its most fundamental level is far stranger than we might have imagined, yet is still describable with incredible mathematical precision. The simple act of observing a beam of light, it turns out, is an encounter with a deep mystery that centuries of scientific investigation have only just begun to explore. Consider the night sky, where every point of light is a star sending photons toward you. These particles of ancient light have traveled for years, centuries, or even millennia to finally reach your eye. From their own frame of reference, that incredible voyage took no time at all. They carry no memory of the journey because, for them, no journey occurred. They are as pristine as the moment they were created. The starlight arriving tonight is a gift from the cosmos, strange, beautiful, and waiting for our understanding. So the next time you switch on a lamp or feel the sun's warmth, remember you are surrounded by one of physics' deepest enigmas, hiding in plain sight, just as it has since the first photon raced from the first star at the beginning of time.